Welcome back everyone. In this lecture we will continue to see some basic properties of root system, and using those properties we will completely classify rank 1 and rank 2 root systems. So, that means dimension 1 and dimension 2 root systems. So, for that purpose let us actually try to understand some of the basic properties. So, we fix phi to be a root system. So, this is a root system. So, I keep writing this tuple phi comma e to emphasize that phi is actually subset of e. At some point we can actually stop writing this capital E, it is okay. So, now what we want to do? We want to understand what are all the possible root system that we have in rank 1 and 2. So, dimension 1 and 2. So, more or less they actually give us all necessary working examples. Okay, so what we do first, we try to understand some geometric constraints that we have using this crystallographic condition. So, let us take some alpha beta inside your phi. Of course, if beta is just a multiple of alpha, if beta is multiple of alpha, then we know that beta should be either plus or minus alpha. So, because of this we assume that this beta is actually not multiple of alpha. Okay. So, what happens if we do not have anything like that? So, then all the elements of phi must be multiple of each other. In that case you can see that using the axiom of phi, so then we must have phi equal to plus or minus alpha, nothing else. So, that means this is the only dimension 1 rank root system, dimension 1 root system. So, pictorially it will look like something like this is alpha, so then this is minus alpha. Okay. So, this is the only dimension 1 root system. So, for that purpose we can assume that the dimension of E to be more than actually 2. In particularly since span of phi is E, so we will have at least 2 linearly independent vectors inside phi. So, we can choose alpha beta such that beta is not equal to plus or minus alpha. So, now just look at the Cartan numbers and then see what happens. So, recall the Cartan numbers, the bracket beta comma alpha is nothing but twice beta alpha divided by alpha alpha. So, this is supposed to be an integer. Okay. But recall that from elementary Euclidean geometry. So, if we take two vector alpha beta, if this is alpha and this is beta, and theta is the angle between alpha beta. So, then we have this nice formula of this cosine of theta in terms of this inner product alpha beta. So, what is that formula? So, recall. So, this norm of alpha and norm of beta times cosine of theta must be equal to the inner product alpha beta. So, this is the formula. So, what is norm alpha? Norm alpha by definition, so norm square alpha is just alpha alpha. So, this is the definition. So, now using this thing we can see that this Cartan integer is actually equal to twice norm beta divided by norm alpha cosine theta. Okay. So, in particularly if we multiply this Cartan numbers related to beta alpha and alpha beta. So, then we can see that we will have lots of restriction. So, this let us multiply this Cartan integers beta alpha with alpha beta. So, then we get it is exactly equal to twice norm beta divided by norm alpha times cosine theta, and then since the angle between alpha beta and beta alpha they are same. So, then we get this is exactly equal to again twice norm alpha divided by norm beta times cosine theta. So, then we just cancel things and then see that this is going to be 4 times cosine square theta. So, since this must be integer, since this is square of something, so this must be non-negative integer. So, this is non-negative integer. So, since this cosine square, it can be at most 4. So, then you can conclude that this cosine square is at most 4, then you can conclude that the product beta alpha and alpha beta, that can be at most 4. So, now let us see whether it can take value 4 or not. So, what will happen if it takes value 4? Suppose 4 cosine square theta is equal to 4, then that would imply that cosine square theta is actually 1. So, that means cosine theta is plus or minus 1. So, that would force that either theta is 0 or 2 pi. So, that means this beta must be plus or minus alpha, multiple of alpha. So, that cannot happen because we assume that beta is not equal to multiple of alpha. So, that means this it cannot obtain 4. So, that means what we could conclude, this beta alpha, the product is actually at most 3. So, this can be either 0, 1, 2 or 3, and we can also see that this kata numbers, both of them, so they are actually integers. So, they are integers. So, now these two conditions actually put lots of restriction on the possibilities of this angle beta comma alpha. So, let us see one by one and then make a table. So, let us see what happens if it actually hits the product hits 0, 1, 2 and 3. So, since these numbers 0, 1, 2, 3, they are all like small numbers and then they can, their prime factorizations are trivial. So, from that we can conclude that the possibilities of this angle alpha beta and then angle beta comma alpha, so those are all very limited. Okay, let us make a table and then see what happens. So, here is the table. So, we just record what happens to this angle alpha beta and then angle beta alpha and the angle between the beta and alpha, which is theta. So, we write here angle alpha beta and then this theta and the ratio between these norms. So, note that if we change the inner product by some positive multiple of the inner product, these kata numbers, they are not going to change because they are being ratio of these inner products. So, it is beta alpha divided by alpha alpha. So, the numbers will not change. So, that means by replacing the positive definite form by any positive multiple of the definite form will not actually change things, okay, because these numbers are the important numbers in the about the root systems. So, now you can see if for example, if beta alpha times alpha beta, if this is equal to 0, then this forces that the inner product beta alpha must be 0. Similarly, so this is the case 1. So, what will be the case 2? The case 2 will be if beta alpha times alpha beta, if this is 1, then this will force that this angled alpha beta is either plus or minus 1. So, we can assume to be this is 1 and the angle beta alpha is also 1, or the angled alpha beta is minus 1 and the angle between beta alpha is minus 1. So, without loss of generality, one can assume that norm of alpha is smaller than norm of beta, because we have only 2 vectors alpha beta. So, we can just compare their norm and then without loss of generality we can assume one is smaller than other. So, now using this information we can just start filling this table. You can see that the possibilities will be if theta is exactly orthogonal, that is beta comma alpha is they are orthogonal, then theta will be just pi by 2. So, in that case you get alpha beta being 0 and beta alpha b is 0, and in this case you can see that this norm beta square divided by norm alpha square, this cannot be determined. So, this is undetermined. So, now what will happen if we take this alpha beta is being the product being 1. So, let's just work it out and then see what happens when it is product is 1. So, you can see that in the first case the beta alpha will be 1 as well as the alpha beta is 1, and in this case you can see that the the norm of alpha and norm of beta must be equal, because this is going to be give us twice beta alpha divided by alpha alpha is equal to twice alpha beta divided by beta beta. So, now if you just cancel things, you can see that the inner product alpha alpha must be equal to inner product beta beta. So, that means the ratio between the norms must be 1. So, that is what we get. So, now you can see that if the angle between theta, okay. So, what it will be? So, in case this both of them are 1, then the product is going to be 1. That means cosine 4 times cosine square theta will be 1. So, in that case you can see that cosine square theta will be 1 by 4. So, in that case cosine square theta will be equal to plus or minus 1 by 2. So, when these numbers are 1, then we will get cosine theta to be plus of, okay, this is not square, this is just cosine theta. So, in the case 1, when beta alpha and alpha beta both are 1, so we will get cosine theta to be off. So, in that case we get theta to be pi by 3. So, you can read it from the cosine table that when cosine theta is off, then that implies theta is pi by 3. In case 2, what will happen? So, when this beta alpha and alpha beta, if they take value minus 1, then again if and only if you can see that the cosine theta will be minus of, in this case theta will be 2 by 3. So, if you go back to the table, you can easily fill that in the first case both the values alpha beta, that Cartan numbers will take 1 1, then the angle will become pi by 3 and the ratio between the norms will be 1. In the second case both values will be actually minus 1 and the angle between the alpha beta will be 2 by 3. So, then the ratio will become 1. So, now again similarly one can do the other cases, maybe I will do one more case and then I will leave the last case for you to check. So, what is the third case? So, the third case being the product alpha beta, the Cartan numbers beta alpha is being 2. So, in this case then what we will have? We will have 4 cos square theta to be 2. So, that will imply that cos square theta is actually 1 by 2. So, that means cosine theta will be 1 by root 2. So, now this is plus or minus cosine theta. So, then you can see that cosine theta is being 1 by root 2 if and only if this angle alpha beta will be 1 and then the angle beta alpha will be 2. So, note that. So, if we compute this angle alpha beta, which is nothing but twice alpha beta divided by beta beta. So, this absolute value will be definitely less than or equal to the absolute value of alpha beta divided by alpha alpha, because we assume that the norm of alpha. So, we assume that norm of alpha is smaller than norm beta. So, that implies this absolute value of this alpha beta, that angle, this Cartan number is less than or equal to the absolute value of this beta alpha. So, that forces that we can take this to be 1 and this to be 2. So, that is what happens when cosine theta is 1 by root 2. When cosine theta is minus 1 by root 2, you can see that this angle alpha beta will be minus 1 and then the angle beta alpha will be minus 2. So, in this case you can see that theta will be pi by 4 and in this case theta will be 3 pi by 4. So, in this case it will be 3 pi by 4. So, then if you just fill it, so what you get? You get so we get in this case 1 2 and then minus 1 minus 2. So, in this case the angle will be pi by 4 and then 3 pi by 4 and you can also see that the ratio between the norms, okay, that is going to be just 2, okay, this 2 will appear as ratio. So, that is because what will be the ratio? So, if you take angle beta alpha divided by angle alpha beta, so then you can see that this is going to be exactly twice beta alpha divided by alpha alpha times alpha alpha divided by twice alpha beta. So, now this 2 alpha beta and 2 alpha beta will get cancelled, then you get this is exactly equal to alpha alpha divided by beta beta divided by alpha alpha, beta beta divided by alpha alpha. So, that is going to be the ratio between these two. So, that is exactly going to be 2 because this is 2 divided by 1. So, that is what this ratio. So, then this will be 2 and this will be 2. And similarly, the case 4, the product can be 3. If the product, if it is 3, then the ratio of this norms will be 3 and then you can see that the possibilities of alpha beta, that Cartan number associated with the alpha beta, that will be 1 and then minus 1. In that case, the Cartan number associated with the beta alpha will be 3 and then minus 3. So, in this case the angle also can be determined. So, you can see that the angle will be just pi by 6 and then 5 pi by 6. So, this is something I will leave it to you to check. This is again not very hard, you can read it from the cosine table. So, this is actually puts lots of restriction on these Cartan numbers as well as the angle between the alpha and betas. Okay. So, these are all the only possibilities, you can see that. So, these are all the only possibilities that we have for the Cartan numbers as well as the angle between alpha and beta and this ratio of these norms. So, now using this table one can immediately conclude the following. So, which is very important observation. So, this observation is actually tells us when we can add 2 roots and subtract 2 roots. Okay. Again whether that will be again root or not. Okay. So, this is very important lemma. So, which we call it lemma 3 in this chapter. So, what is lemma 3? So, you start with alpha and beta in phi. So, what do you want to know, whether you can add this alpha beta or subtract this alpha beta, this is something we want to know. So, what I mean by that, whether if you add this alpha beta, whether it is again a root or not, that is what we want to know. So, let us see what happens. So, you can assume that safely that beta is not multiple of alpha. Okay. So, in this case we just take this inner product alpha beta and then see based on that inner product what we can conclude. Of course, the inner product is 0, then we can't conclude anything, because what we saw, so in that case they become orthogonal to each other. So, then it will look like something like this. So, this is going to be alpha, this is going to be beta, and the ratio between the norm of alpha and beta also cannot be determined. So, in particularly, for example, if you use the reflection corresponding to alpha or beta, then you can see that S alpha beta will fix beta and similarly S beta of alpha will fix alpha. So, in particularly when alpha beta the inner product is 0. So, then if we take phi to be this plus or minus alpha plus or minus beta. So, this is going to be already a root system. So, in this case we can't conclude whether we will be able to add or subtract. Okay. But there is a possibility of adding, okay, but we will see later some examples. Even orthogonal roots can be added to get roots, but we want to conclude something concrete. For that purpose we assume that the inner product of alpha beta is actually non-zero. So, if it is non-zero, then there are two possibilities. One is the inner product is positive or it is negative. So, if it is positive, that means the angle between alpha and beta, they are strictly, the angle is strictly acute. In that case we will be able to subtract alpha from beta, that will be again element of your phi. In case this inner product is negative, that is beta alpha is negative, then we will be able to add. So, that means alpha plus beta will be a root. Okay, let me write it here. If alpha beta is positive, so then alpha minus beta is again a root. If alpha beta is negative, so then alpha plus beta is a root. So, these are all the conclusions. So, of course, when alpha beta is orthogonal to each other, then we may not conclude anything. Okay. So, here is the proof. So, we will just prove the second statement. The first statement will be similar to that by applying for beta to minus beta. Okay. We take alpha beta to be less than 0. So, assume that alpha beta is less than 0. So, then in this case we look at this Cartan number. So, you can see that the Cartan number alpha beta or beta alpha from the table. If you go back to the table and then see what happens if beta alpha negative. So, you can see that the only negative things are happening here, here, here and here, and when norm of alpha is smaller than norm beta. So, then in all those cases we are getting minus 1. So, that means if we do not assume anything about beta alpha, if we do not compare the norm of beta and norm of alpha. So, from this information that the inner product beta alpha is being less than 0, from that information we can immediately conclude that either the Cartan number alpha beta is minus 1 in case of norm of alpha is smaller than norm of beta, or otherwise the Cartan number associated with beta alpha. So, that will be minus 1. So, that happens in case of norm beta is smaller than norm alpha. So, in any case, so one of them will be minus 1. So, let us consider alpha beta is being minus 1. So, in this case what we will do, we just apply S beta of alpha. So, if we take S beta of alpha, you can see that this is going to be alpha minus the angled alpha beta comma beta. So, in this case you can see that since this is minus 1, this is going to be alpha plus beta. So, this is going to be root because S beta of alpha is again element of your phi. So, similarly, in case beta of alpha is minus 1, so then you can conclude that S alpha of beta is going to be beta minus the angle beta comma alpha which is going to be beta plus alpha. So, it is going to be again a root. So, in both cases we can conclude that alpha plus beta must be a root. So, now if we go back to your first case, you can replace beta with minus beta, then you can conclude that alpha minus beta is negative. So, then that implies alpha minus beta is phi. So, that means the second statement implies first statement. So, this lemma is very useful lemma. So, in particularly we can conclude many interesting conclusions from this lemma. Towards that, for example, like we can actually classify rank 2 or dimension 2 root systems using this lemma. But before that, let us make one important application, which is about the alpha string through beta. So, in the theory of semi-simple Lie algebras, we saw that the roots of these semi-simple Lie algebras with respect to a maximal toral subalgebra satisfies the property of this following property, which is if you take alpha string through beta, that must be unbroken. But right now we are working with abstract root system. So, we may expect a similar property to hold here in the abstract root system. So, let us see whether it holds or not. So, that can be proved using these elementary properties of roots. So, that is what we are going to discuss now. So, you take alpha string through beta and then we will claim that this must be unbroken. Okay. So, first of all, what is the meaning of alpha string through beta? So, you fix alpha and beta inside your phi, and as before you assume that beta is not multiple of alpha. Again, if it is multiple of alpha, then there is nothing to say about alpha string through beta. So, then what we are interested in? We are interested in looking at all possible roots of the form beta plus I alpha. Okay, we are interested in beta plus I alpha, which are all roots. Okay. So, you call this as before a set S of beta alpha. So, S of beta alpha is defined to be those beta plus I alpha such that where I is coming from integers and beta plus I alpha is again a root. So, this is the set we are interested in. So, we want to claim that this S of beta alpha is indeed unbroken, it corresponds to an interval. Okay. How one proves this? So, since phi is finite, so one will be able to always choose these largest non-negative integers R and Q such that beta plus Q alpha is in phi and beta minus R alpha is in phi. Okay. This is something we can do. So, let R comma Q. So, these are all two non-negative integers. So, again largest possible non-negative integers such that beta plus Q alpha. So, this is in phi and beta minus R alpha, this is also in phi. So, these two ends are actually in phi. So, that means what? That means if we take beta plus I alpha is in phi, so that should imply that this I is coming from between minus R to Q. So, that is what it means. Okay. So, now for some reason let us say this S of beta alpha, so this is broken. So, what is the meaning of that? So, we claim that, so our claim is S of beta comma alpha is exactly going to be equal to beta plus Q alpha, beta plus Q minus 1 alpha all the way to beta minus R alpha. So, this is our claim. So, if this claim is not true, that means S of beta alpha is broken. So, that means what will happen? So, if you read it from minus R to all the way to this plus Q, so then you will be able to find some S such that, so you go from Q to go down Q minus 1 and so on some S. So, this Q alpha beta plus S alpha, so that may be in Q, that may be in phi, but when you go down to S minus 1, that may not be in phi. Okay. So, you can choose this S such that beta plus S alpha, this is in phi, but beta plus s minus 1 alpha, this is not in phi. So, such as we can choose by starting from Q2 and then going down. Similarly, if you start with R and then go up, so then we will be able to choose one P such that this P is in phi, but P plus 1, this is not in phi. Okay. So, we can choose this P. So, this must be definitely less than S, such that this beta plus P alpha. So, this is going to be in phi, but beta plus P plus 1 alpha, this is going to be not in phi. So, these are all the conditions that we get. Okay. So, we will be able to always choose, because we have assumed this chain S of beta alpha is unbroken. So, you just read from left to right and then right to left. So, you will be able to come to some stage where some part of the chain is not there. Okay. So, this is what happening. So, then you can actually see that since this beta plus P alpha is in phi, but beta plus P alpha plus P alpha, this is not in phi. So, from this we can conclude that beta plus P alpha, when you take inner product with alpha, this has to be always greater than or equal to 0. If it is less than 0, we will be able to add alpha. So, as we cannot add alpha to beta plus P alpha, and using this lemma 3 we conclude this. Similarly, we also conclude that beta plus S alpha times alpha, this must be non-positive, as we can't subtract alpha from beta plus S alpha, okay, because beta of S minus 1 alpha is not there. So, now you just look at this inequalities and then rewrite, then what we get. So, we can easily conclude that this beta of alpha minus, so this has to be less than or equal to P times alpha alpha. So, this is what first inequality says. The second inequality says this minus beta of alpha should be at least this S times alpha alpha. So, that is what the second inequality says. Now, since alpha alpha is positive, so then this implies that S is less than or equal to P, which is a contradiction, because this the way we choose on P and S, that guarantees that P must be less than S. So, this proves that this chain that we are talking about must be unbroken. So, that means this S of beta alpha should contain all these elements, like beta plus Q alpha to beta minus R alpha. So, this is proves S of beta alpha is equal to beta minus R alpha to beta plus Q alpha. So, this is what we do. So, now note that if we apply this reflection S alpha, so that is going to just add some multiple of alpha to each root. So, in particularly if we take this alpha string through beta, if you apply this S alpha, so then it is going to add or subtract some alpha with this given root. So, since these are all the only roots that are there in phi, so that makes this S alpha to leave this S of beta alpha invariant. So, S alpha of S of beta alpha should be exactly equal to S of beta alpha. So, now geometrically it is very clear that this root string will be reversed when you apply S alpha. Again, algebraically it is not hard to compute and see. So, when you apply S alpha on this beta plus I alpha, you can see that this is going to be exactly equal to S alpha of beta minus I alpha, which is going to be beta minus this angle beta alpha plus I times alpha. So, when you take plus I, it is going to reverse it to minus this beta alpha, that Cartan number associated with that, plus I. So, that means we see that S alpha of beta plus Q alpha must be equal to beta minus R alpha. So, this forces that beta minus the angle beta alpha plus Q alpha, this Q times alpha will be equal to beta minus R alpha. So, now cancelling beta beta and then alpha alpha, you can see that. So, we get exactly equal to R equal to the Cartan number beta alpha plus Q. So, that means R minus Q will be exactly equal to the Cartan number beta alpha. So, from this you can see that. So, this is something we proved using SL2 theory when we consider the roots that comes from semi-simple algebra. But here by just looking at the alpha string through beta and then understanding some basic properties of the roots, we are able to prove this result. So, most of the properties that you see about roots that are there in finite dimensional semi-simple algebra, that can be reproved using whatever axioms that we have assumed about the set of roots. Okay. So, this is again very interesting exercise to reprove something that we already proved using SL2 theory and so on, in using some elementary ideas of root systems. Okay. So, what we can conclude from this equation, you can immediately conclude that since this angle beta alpha, this is going to be a Cartan number, and absolute value of this Cartan number is going to be at most 3. So, that actually immediately says that the root strings are of length at most 4. Okay. The root strings are of length at most 4. So, all this we are getting it from one information, that is that Cartan numbers are integers. Okay. That actually puts lots of restriction on geometric constraint on these roots. So, from that we can see that even this integrality conditions the integrality properties, that alpha string through beta and all will have lots of restrictions. Okay. So, I will actually stop here. So, whatever we have developed so far about this basic properties of root systems will be used in order to actually classify rank 2 root system. So, which I will do it in the next class. Thank you.